Hi, I'm Mark LeMay, and I'm going to tell you about some of the work in progress we're doing to develop a dependently typed language with a runtime proof search. So why would you want to do that? Well, I'm going to try to motivate it with a little example that I think probably everyone who's watching this has done at some point. I was doing it myself recently on another dependently typed language I was working on, and I converted everything to Agda so you wouldn't have to deal with the horrible syntax. Uh, so as you do, first you define the natural numbers, define quality, define addition, then you want to prove some simple fact about the natural numbers and addition, for instance, that addition is commutative. It's easy to write out the fact. Uh, and you know it's going to be inductive, so you got to work out the base case. And as you work out the base case, you realize that you need the successor to preserve, if the inputs to a successor are equal, then the output is equal. So you need to go through and prove that. That gives you the base case. Then you need a couple more lemmas for the inductive case. So for instance, you need to prove transitivity of equality, and then you need to prove this kind of awkward lemma that will pull the successor out of one branch of addition into the top of the other branch of addition, which itself uses that other lemma. And then you can build up your proof that addition is commutative. So what I don't like about this style of working is that it's very bottom up. We can't, if this were a realistic situation, probably I wouldn't even care about the proof of addition being commutative. I would want to use that as a lemma for something much more interesting. But because of the way dependent type systems tend to be structured, you need to work from the bottom up and build up all your lemmas if you want to have any assurances of anything. Now, for each of the lemmas I just quickly demoed, we can think through the Curry-Howard correspondence. What does that lemma do as a program function? And in each of those cases, they all do basically pretty dumb things where they just spit out REFL. So why do I need to go through all the work of telling the computer all the different ways, like specifically how to spit out this one thing, when it's always the one thing? Uh, so what we're proposing is that there's a new piece of syntax that will just run a proof search on whatever inputs you give it to find the type when you need it. And then you can test that runtime behavior like you would any other function. So this ends up being a little bit more involved than you might think. So here's the design of the system we're working on. We have a type checking phase, which gives us some minimal guarantees, and exploration testing phase, where the functions or proofs are tested on inputs, and we discover where admits are being used, uh, what types admits are being used on, and then finally we have a runtime phase that will use the admitted type, that will evaluate as normal in a call by value way, and will use the pre-computed types that the pre-computed terms that the exploration phase will hopefully find. So type checking isn't too bad. Probably it's not terribly surprising that you can make a type system with type soundness out of this. Uh, so we add a constant piece of syntax with a typing rule that lets it inhabit any type. we also allow some definitional qualities as long as they're closed values, and also we want them, we insist that they be consistent, because inconsistent equalities can lead to bad behavior in a way that is obvious in retrospect but wasn't when we started out. Then at the end of the proof, when you're saying uh, so when you actually evaluate one of these admits, you kind of cheat the proof and you say give one of the closed values or just non-terminate. And the guarantees we would like from this are that for every ground type, the ground values work as expected. So if you have a term, which is a sigma type which is a dependent pair of natural numbers, a dependent pair of a natural number and a proof that that natural number is even, if it terminates, then the first number will be even. This is why we are insisting on a call by value evaluation, because in a call by name evaluation, this wouldn't be true. You could stick 3 in the first position and then non-terminate in the second, and then just spin forever trying to find a proof that 3 is even in the second position. This is pretty similar to some of the early Trellis work, where they had non-terminating recursion, and you have to do similar things. For the exploration phase, things are a little bit more complicated. The example I gave in the beginning was a little bit misleading. If you're going to add this admit syntax, you have to, and you want to explore over all the possible execution paths of your program, you've got to handle branching behavior, higher order inputs, dependent types can possibly interact. And at the specific example, when you're outputting a equality at nat, it's nice and decidable, where there's no guarantee that a type will be inhabited in a decidable way in general. So to look into this, I'm going to give another example at simple types. So if we want to explore this program and find the admit being used, one way to do it would be to lazily expand the graph of all the inputs to this function. So we have a function f that takes in g. If g given 2 equals 3, we'll do some stuff. If it's not equal to 3, we'll give back 4. If g given Sorry about that, my microphone just chopped out. If g given 3 equals 4, then we're going to need to record this use of our scary syntax, and otherwise we'll give back 7. So we can evaluate this program, and when g needs to figure out what it's doing, we can test it on different possible outputs. So here we say when g is equal to g given 2 equals 0, then this whole thing, f of g, is going to equal 4. If we explore g at 2 equals 3, and g of 3 equals 0, then f of g will give us 7. And if g of 2 equals 3 and g of 3 equals 4, then this will tell us that we need to do a proof search for an int, which will not be all that hard. Now this hints at more complicated issues that can come up. For instance, if we change the code like this so that g of 2 equals 3 and g of 2 equals 4, this admit branch will not be possible. So we probably shouldn't explore it. And of course, because this is a matter of equality, higher order functions are not, it's not going to be convenient to figure out when higher order functions are equal. So for instance, depending on which side of the plus the 0 is on, the dependent type theory may think this equality is obvious or not. So to work around this, we have, this is the exploration strategy we're trying to use. If the type is a pi type, then we're going to, or pi type or dependent function type, then we're going to instantiate all the free variables until we get to a ground type. We're going to then we're going to attempt to normalize it with those free variables. And in the course of normalizing, if we need to give an assignment to, if there's a branch where a free variable needs to decide its behavior, first we're going to resolve the type, possibly by filling in the free variables in the type. Then we're going to try every consistent possible assignment at that type. And if any admits are observed, then we're going to jump out of this and report all the assignments we made. And when I say consistent assignment, it means that if there's a way to differentiate, a consistent assignment is any assignment to a free variable where any argument can be differentiated. So if it's a ground type, for instance, you can differentiate it by the constructors. If it's a function type, you might need to instantiate, you might need to apply arguments to it and do further consistent assignments. So for instance, the function lambda xx can be differentiated from the function lambda xy, where y is a free variable, by instantiating y at 2 and applying 1 to each function. That'll give us a ground type where you can tell 2 is different than 1. Yeah, so even in this pretty horribly simple exploration algorithm, there's some kind of quirks in it. We believe this is a complete algorithm in the sense that if there's a way to evaluate to an admit, we'll find it. It's not sound. For an example, that it's not sound. So if you're familiar with PCF and parallel OR and PCF, this is basically that example translated to our system. So there are things that our system would warn about that aren't necessarily, that you wouldn't be able to program into the program or program in the language. I was a bit surprised when we started this that there wasn't more research into basically exploring higher order functional programs. So if you're aware of any, please let me know. After submitting, we did find out that you and Bobby Findler and some of their collaborators have been working on something similar at simple types using canonic testing. So that's very interesting, and they've got much nicer proofs of a lot of these properties. So given all that work, we can hopefully run things. We would like to have more insight in how this works out, but since the implementation is still in progress, we can't say for sure that this is a good or bad way to actually run things, though we're a little bit afraid that admit will give users the wrong impression of behavior, because it won't choose the best instantiation of a type, it'll just choose an instantiation of the type. So for instance, if you want to find a natural number and then find a pair of a natural number that's less than the original natural number, well, it's going to probably start out at 0. So this will not type check. Or sorry, this will not terminate, even though there's an obviously good choice of a to 1. So we're currently, so the work is still in progress. Where things are going slower than hoped for kind of mundane software reasons. Once we get the components better tested and plugged together, there still needs to be a bit of user interface work to communicate all this information back to who's ever using the system. But there's also some like very interesting ways I think you could take this. I've been looking a lot at the research into combining dependent types and effects recently, and it seems like this could be, or it seems like you could make a very compelling non-deterministic effect system with dependent types. So if anyone has any thoughts about that, please let me know. Uh, I would really like to make the search algorithm a little bit less dumb. So by incorporating techniques from logic programming and constraint logic programming. Uh, oh yeah, and there's one other like really cute thing I think you can do with this, where if you have a reasonable system for doing all the, for doing admits and testing admits, that you could inject admits into the programs when type checking fails at values, and simulate kind of a gradual typing behavior. So for instance, if you're looking for if a vector of x plus y is not obviously equal to a vector of y plus x, then you just stick in an admit for that identity type, and if it works, it works. If it doesn't, it doesn't, and if there's some subtle problem with your addition, that'll get uncovered through testing. So I'm going to switch things around a little bit because of the weird format, and I'm going to ask the audience questions here. So the one thing that really makes me, one of the things that really makes me nervous about doing this is that we break basically all of all normal parametric reasoning you would get. So for instance, uh, for all A arrow A is not the identity here. It also doesn't fail in kind of the normal Haskell way, where it's always going to terminate. It's actually pretty weird, and you can kind of guess what, it's very weird. I haven't found any actual problems that come from that, but if still makes me uneasy, so if anyone knows how that would work, uh, yeah, I don't know, it's just kind of mind-boggling. Uh, If anyone has any thoughts about of how you could get a runtime proof search as an effect system, I'd be very interested in that. And finally, we're fudging a lot of type universe stuff right now, to the point where on the theory side we're pretending there's no type level quantification. In practice, we're doing type and type, and it seems a little uneasy. So if there's any thoughts about how to do this with type universes, I'd be interested in chatting with that. And finally, and then we'll open it up to the traditional questions if you have any questions from me. Thanks. I'm looking forward to hearing all of your questions on Zoom.